All right. How's everybody doing? It seems kind of low energy in here. Maybe it's because of the dreary weather outside. I don't know. I always like rain. So, huh? No, no, no. I love just walking around in the rain. Maybe I'm weird, but okay. We're on AWS just because I don't have anything to make up today. We only have one more day before identity. So we only have three class periods left, including this one. So what we're gonna do during Dead Week is on Tuesday next week, I will, well, over the Thanksgiving break, I will write the final exam and we'll do a final exam review on Tuesday. And on Thursday, we can have a party or do whatever we want. Yes. Final exam is, I don't know, it's on the schedule somewhere. Let's see. It'll be in this room. Um, Tuesday, Thursday. Okay. Looks like the final is at noon on December 12th. Yeah, 12 to 2. So you have 2 hours. I'm not gonna make the final exam that much longer than the midterm because I think I made the midterm a little bit too long because nobody finished early. So I'm not gonna increase the size of the final by that much compared to what the midterm was. So hopefully you all will have enough time to finish. So I don't want to have to give you a 15-minute extension. Any question on those pieces? Okay. So after project one and after the first exam, I have gotten a lot of requests for an extra credit opportunity in this class, and I need some ideas. So, do we want to collectively brainstorm? What, besides project two, which is the only other project you're gonna get in this class, what would you want to have a project on? Where do you feel like the gaps in the projects have been so far? Is there a piece of Spark that I haven't covered yet in either the projects or the exams that you want to touch on?
What we don't know, right? Like
Sure.
some be able to make sure that we do analysis with what I know in Spark. And I feel like honestly when it comes to mathematics in Spark, there's a lot that I don't, right? And maybe you feel like like you know or not should at least know what to look at.
That's the thing is you don't have to walk away from this class knowing everything, but I hope you can walk away from this class knowing how to Google stuff. Either that or know the difference between what's true and what's BS when you ask ChatGPT something.
So as part of the brainstorm, I would love, and I don't have a specific example of what I was doing for this, but I have found that when we try to do things in a large scale, trying to test with what I'm doing in usable is very, very different than when I'm doing data manipulation classes. Like it's easy to write something and then just eyeball it and check and say, oh, we got 18 under that. And so I feel like I'm just barely starting to develop those types of skills. That is hope to me. Like it feels much more when we have a large scale, like what we're doing is a black box. Like, okay, I just was taught to go do all of these things. Oh, that's right. So I'm learning to check things with counts,
Yes.
right? Trying to figure out different ways, but it's fundamental. My experience is fundamentally different than doing things in Canvas where I can just say, oh yeah, that all makes sense, right?
Yeah, I mean, to a certain extent, you can do that in Spark. Like you can look at your results that you're getting in Spark kind of row by row if the nature of your operation permits you to check your work that way. You can kind of do that in Spark, but you definitely can't check the whole thing. You can't check the whole thing that way because there's too much going on. And yes, you'll figure out that when you're trying to do just some basic debugging and sanity checking in Spark, just looking at the count of things is so useful. You know, like when you join the redirect table and the page table, you look at the number of rows and you're like, wait, there's 14 million, but there's supposed to be 60. Why? You can say, oh, I did the wrong join type. Oops. But you're not going to catch that unless you at least look at something like the count. So building up an understanding of what you would expect, even just at a really basic abstract level, can keep things flowing smoothly. The alternative is, what I'm making you do in this project right now is creating a synthetic data set. And that's the harder and more rigorous way to do things, but it's also the more reliable way to do things. And especially when you're creating products and things that actual people, customers will use to solve their problems, you need to make sure that your data processes are robust and are well tested because Spark is inherently hard to test, especially at a large scale. And just remember that there are basically like two phases of testing something when you do a large scale data pipeline, right? You can look at the mechanics of how all the data is manipulated and make sure that the code that you're writing does what you expect it to do, or what you tell it to do, or what you want it to do. You would create your synthetic data set to test for those different cases, just like how you would in a normal test suite with a normal piece of software. The other longer, more arduous, more difficult process is once you've made sure that your code is doing what you want it to do, you have to make sure that what you want it to do actually works, because that's a totally different question you're asking. Like, for example, we have an identity building pipeline at Count. We have this graph algorithm that goes through a graph and designs and creates boundaries around different groups of vertices in this graph. And that's our community detection algorithm. So these groups of vertices are what we consider an identity at Count. And, we can create a synthetic data set that goes through all of our code and outputs the identity delineations we expect, given what we're telling our algorithm to do and given what the input data for the synthetic is. We can make sure it does all that correctly, but that's different from testing whether the actual algorithm works, whether the actual algorithm is creating good quality identities. Because where you draw those boundaries between vertices in the graph really matters when it comes to deciding whether those groupings are good or not, right? We don't have really any mechanism to test that. We can't use synthetic data because you have to use real data because that's an accuracy metric, right? You can't use fake data for an accuracy metric. You have to use real data. And we don't have a signal. We don't have we don't know what the right answer is. Because if we did, we wouldn't need to do this thing in the first place. We would just use the groups that we already know are the right answer. So it's just guessing. And so what we do is every time we run our identity pipeline, we take a few real life cases from the real data that we know are correct. We make sure that the results map up with that. And if they match up, then we can say, all right, this entire run of the pipeline is decent because this very small subset of data points turned out okay. That's all we got. Data science is hard when you don't have data. Hmm.
You haven't done anything with machine learning.
That's true.
In other classes, we're going to spend a lot of time on actually learning like options for library and Spark-based.
You sure you want to use Spark ML? I'm not sure I want to make you use Spark ML. The problem with Spark ML, so Count has our primary machine learning model that we use for detecting credit card fraud, and that is called OmniScore. Is that like available on Count's documentation? Count OmniScore is a transaction safety rating, and this is a score that is generated by a random forest classifier. OmniScore is literally just a random forest classifier in Spark, and it takes 2 lines of code to train OmniScore. And so the problem that we have with OmniScore is it takes 2 days to train this random forest classifier. We have what 120 million input rows in our training, and we spin up a giant Spark cluster, and it takes 2 days to train this model. And so I'm looking at this and I'm like, okay, this is some VS. We got to be able to do better than that. 120 million is a lot of rows, but it's not like that many rows. It's not crazy. We're not doing anything insane. We can do better than this. And so my working theory was that Spark ML is actually kind of garbage and does things in a really inefficient way because for a random forest, you have to constantly shuffle and sort all of the data so you can find the splits that you want to do. So you can find thresholds for the splitting and the decision trees. So my working, conjecture or hypothesis was that this is a really inefficient way to do decision tree learning, to train a decision tree. And so what I did instead was I started a giant hulking EC2 instance with 1.5 TB of memory, and I loaded all of our 120 million rows into memory, and I ran scikit-learn random forest classifier train on it. And it finished in 20 minutes. And it actually produced a decent model that was maybe slightly better than the OmniScore model that was produced with Spark. At least according to, yeah.
Okay, random forest is an ensemble of decision trees.
It is.
Would Spark not be creating the decision trees per partition as in your aggregation then would automatically shouldn't that be fast?
I'm confused on the question.
Of all the different decision trees. If it's creating a decision tree per partition,
No, it creates a decision tree. It creates one decision tree on the entire data set.
we make it not. Doesn't that seem like it should be really efficient?
Well, then you would just be doing a bunch of scikit trainings kind of independently and then coalescing them together. Not really. It's the entire decision. All of the decision trees are being trained on the same data. All the decision trees are trained on all of the data. Yeah. So it's like every split in a decision tree node, the training algorithm selects a subset of features, and it's usually the square root of the number of features. So if we have 100 features in total, it'll select 10 features and then compare, the impurity gains or the impurity loss from those 10 different features, and it'll pick which of those 10 features to split on.
But the reason we were only taking some of those features, you could also do that by just taking different samples of the data.
You could.
You could train all of them single nine.
You could, but what I think I would rather do is just take all of the data and then train it on a big network.
So I see, but it just seemed like, anyway, smart thing. handle ensembles, right?
I mean, it could, but at that point, I don't think you would even need Spark to do that. You could just partition the data manually and then send it out to different EC2 instance, train a bunch of different models independently, and then create your ensemble from that. Spark wouldn't really be doing anything all that novel. It would just be kind of an orchestration system for the whole thing, which maybe that's the only thing that we want, but it's also not that complicated.
It's orchestrating, sending things and how you have to literally and you have to.
Yes, but it's the coordination that makes it complicated because you are referring to a style of programming that a framework called MPI makes you do. Nope. And so MPI is interesting and it's a distributed processing framework in kind of the same vein that Spark is, but instead of handling a lot of the distributed communication for you, you have to decide exactly which machine to send the data to in MPI. It's so much more complicated. You have to handle all of the communication yourself. But, in the example that we're talking about, which is, splitting the data up into a bunch of different partitions randomly, and then having each machine train a decision tree on that subset of data, and then just have the ensemble model be a bunch of those decision trees, that's not hard to do manually. Because the only thing that we would have to do is, create the code to train something on an EC2 instance. And then in the configuration for that EC2 instance, you're going to be like, okay, we're going to point you to this S3 bucket, get 10% of the files from this prefix, bring them in and train a decision tree on that. And then another EC2 instance, okay, you're going to get a different 10%. And another EC2 instance, you're going to say, get another 10%. So you can do all that independently and it wouldn't be that complicated to coalesce them together. But when you're working on a piece of code that requires high levels of coordination between all of your machines, then things get complicated. Because that example of you have a bunch of different machines training their own decision trees independently of each other and not really doing anything else, that doesn't really require any coordination. We can do that all in parallel, and we can probably even do the coordination ourselves if we wanted to.
So there's spikes, machine learning, different other kinds of models to work with me that needs to put them with.
I don't know. I don't have a whole lot of faith in Spark ML. It depends on how the training algorithm works. We've talked briefly in this class that random forest classifier might be an unfair example because it requires so much data sorting, and sorting is something that is especially hard to do in a distributed system. So it might not be fair to be bashing Spark this much. But at least for this particular use case, um, at least our preliminary experiments at Count doing the random forest classifier in Spark versus doing a random forest classifier with a similar data set size in scikit-learn. If you can do it in scikit-learn, do it in scikit-learn. That is kind of the lesson that we've learned here. Questions? That goes for everything in this class, actually. If you don't have to use Spark for something, don't. Spark is a pain. You've all learned that in this class, if nothing else. So if you don't have to use Spark for something, don't use it. That goes with all distributed systems. Just remember that making something a distributed system inherently makes it at least 10 times more complicated. I bet a lot of you, when you got into this class for the first time, are basically saying, Spark data frames, why can't we just use pandas? And my answer is yes, use pandas if you can. or some other local data frame. I don't know. Maybe we could do ML. Problem is we don't have a data set. I'd have to get creative with coming up with a data set. Other thing that we could do, we could, that might be interesting. I've been thinking about this for a while because this was the question that I saw the most people struggle with in the exam. And um, I did give lots of examples for it, but I do feel like we only really covered it in kind of an abstract sense, and we never actually did this. Maybe we could do this. Maybe that would be the extra credit assignment. This is what I'm kind of leaning toward is you can actually make your own Spark aggregation function for real this time. And then you can register it as an aggregation function and then call it from PySpark. You'd have to write the code in Scala though. Yeah, but you can't use user-defined aggregate functions in PySpark. You can't define them. So the interface I gave you, for the Python classes, that was kind of like a made-up corollary to what you're supposed to do here. It's not something that PySpark actually offers. And so you can see the code kind of looks the same. And since I showed all of you how to do, I would probably just have you do the mode. And since all of you know how to do the mode, most of the challenge here would be getting the Scala code to run and then connecting it into Spark and making sure, all the pipes flow into each other properly. So the challenge would be getting the infrastructure running rather than actually writing the code. Because writing the code is easy. So this is what I'm kind of leaning towards, unless somebody has another idea. You guys have an idea? Huh? No? This is good. Help me out here. We got to think of something. I don't even know how hard this is going to be because it's been so long since I've done it. And I want it, so I can't give you a demo, and I'm not going to assign it after the break because that's a little bit late. So if I do assign this to you, keep in mind it's something I don't know how hard this is going to be. Every other project I've given you, I've completed before I assign it to you, so I know how hard it's going to be. I don't know with this. Are we all still okay with that? Speak now or forever hold your peace. Hmm? Well, yeah, the challenge here isn't writing the code. Writing the code is easy. It's getting it to actually work in Spark because you have to connect things together. You have to write this code in Scala, which I'm willing to bet most of you have never done before, is written code in Scala. You have to compile it into a jar. You have to reference that jar from EMR or wherever you're reading your code from. And you have to make sure that EMR or your Spark section actually knows about this thing's existence so it can use it. And you have to reference it properly. So you have to make sure all these things can connect together. So it's a lot of unknowns. And I have done this before, but it's been a really long time and I don't remember how I did it. So these are uncharted waters. So if all of you are okay with this being your extra credit assignment, then I'll write up a spec for it and publish it at some point, either today or tomorrow. So you're saying you literally just want another project for the Wikipedia data? Okay, what would that be? So it would have to be a Spark concept that we haven't already covered. So I can't just ask you to do something that's going to require more joins or more iterative graph algorithms because we're already doing that in projects 1 and 2. It can't be something that requires you, you know, to do automated testing because I'm already requiring that for project 2. So it would have to cover ground that we haven't touched in a project. No point in doing the same thing twice. Not in what? Well, I mean, you can't though. Well, you can't. You have to do it in Scala because that's how you get it to actually run in Spark. Mhm. Conceptually, it's easy. Um, non-conceptually, it's hard because you have to plug a bunch of things in, right? Yeah, you have to learn Scala. You have to know what this means. Does anyone know what this means? This part? These are generics. Is anyone familiar with generics?
Professor, are you sharing your screen?
Excuse me, hold on. I have chat saying something. Hello?
Hello, are you sharing your screen?
No, I am not.
Okay.
Okay, I'm sharing my screen now. Thank you.
Okay.
So these are generics. And generics are a feature of a statically typed language. And those of you who have never written code in a statically typed language before, this might look a little strange. How many of you have written code in a statically typed language? Java is a statically typed language. How many of you know what a statically typed language is? Okay. So it's probably not going to be as easy as just writing the code. You have to figure out the language too, because it's quite different than what you're used to when you're just writing Python. There are extra things that you have to consider. Statically typed languages are generally a more robust way to write code than something like Python, which is what's called dynamically typed. Another thing in here that's going to make it challenging is Scala notebooks, although they do exist, are much harder to use. And so if you needed to try something over and over, you would probably just have to resubmit a step to the same EMR cluster. You can submit multiple steps to an EMR cluster. As in, you can tell an EMR cluster if your step fails to continue running so you can submit another step. You can do that in EMR. So at the very least, doing that will improve the time that you spend developing different iterations of this and enable you to fail faster. So you can try stuff more often. Alternatively,
so this is actually most points towards the different data sets and then on this budget, so they have to be different. We're really the main connecting that, and so at this one, using picture of um, Twitter, and from our world of data, I'll put in the teams, this one's going on that. And then slowly combining, trying to get the data sets and all sorts of questions. Which regions may look for the next best. So now my first action to do that. So like that would force us to be able to figure out how to load in data, how to analyze what it actually means, and answer questions and you might know about it. That seems very practical.
Well, sure, it's it is practical, but the key thing that we have to keep in mind here is mechanically, would you be doing something in Spark that you didn't already do in Project One? You're dealing with different data.
What I could be doing is translating business questions about getting business.
Okay.
So if it wants to know, is the trend of global COVID-19 discussion going on with it? Okay, well, how would we translate that into technical specs within the data? Right? Having it's called, how would we do that?
Maybe. But that also sounds like, kind of what I asked you to do with mutual links, because I did very little to describe how you want to do mutual links. I described what I wanted and what it meant, but how to get there was up to you. And that's the other thing is like I'm really satisfied with everyone's like actual Spark code. And so I don't really feel the need to test you on that. The only thing I think we haven't covered, at least in detail, is UDFs, but those aren't that hard. It's really just writing Python code. That's kind of all it is. It's writing Python code and then plugging it into Spark. And so do you think that answering any of those questions that you listed off would require the use of the UDF? If that's the case, I can take a look at the data.
You could actually, it has data here, right? Questions and require the UDF, right? We can, or we can just say we have to use the UDF and finding one in
Okay. How much data is there? Well, the ideal scenario is you want to use a UDF only when you have to. So if you can find a way to do something without using a UDF, you should do it. So if I would rather not go in the opposite direction where I would say you could do this without a UDF, but I'm going to make you do it with a UDF anyway so that we learn how UDFs work. I would rather have you do something that requires a UDF in order for you to do because it's too specific. Um, so if we can find something like that, that would be interesting. The data set also has to be large enough. We would probably need several dozen million rows at least in order to make it viable.
I think it's yes, you told me, yes, what you wanted. In the first one, tried me watching on page different. But even our side, that was the answer some is
Not really. I just thought it was cool.
yeah.
Sure.
That works with the
Yes.
but I feel like that's not the same thing as having some givers person come and say, I don't know what you're doing on this.
Correct. What I gave you is, yeah. Correct. What I gave you is lower level and more specific, but that's kind of a requirement when you're assigning something for a project because we need to be all doing the same thing. We need to all have the same end goals. You know, you have a business person come in with a proposition and this person asks five different people what the solution is going to look like, and they'll wind up producing five completely different things that will do completely different. Rista, did you have something? Oh, okay. You look like you had something to say. Okay. So yeah, finding a decent like real world data set to use for this class was really hard because it has to be large enough. I wanted it to be understandable. I wanted it to be something that you kind of interacted with in your daily lives so that you could maybe appreciate its impact or understand what it meant when you looked at it manually. Because a lot of data sets, especially larger ones from like social media and stuff, are just totally anonymized or sanitized or filtered. And in that case, they're not nearly as interesting or useful. I remember when a we did a study on the Facebook graph in this class. You had different people who were Facebook friends, and every person was given an identifier, a number, but that's about it. So we don't know anything about these people or the nature of their interaction. We just know the numbers. And so that's an anonymized data set. So finding a data set that checked all of those boxes was not easy. Alternatively, what we could do for this extra credit assignment is I will have you figure out how to move the data from the Wikipedia dumps into S3. That was something we didn't cover in this class, and that's something that's also important to know how to do. But it's also a massive soul-crushing pain that I wouldn't wish on my worst enemy. So that's the other alternative. And I'm not going to give you detailed instructions on how to do it, which means you'll have to navigate the Bermuda Triangle on your own. That does not sound like an exciting prospect, does it? And also, it means that those data imports take like 2 days to run. So you'll have a lot of time to like try different things. And it also means that I will have to, if you attempt this, we'll have to very closely monitor your AWS resource usage to make sure you're not doing anything that you shouldn't be doing. Because having an EC2 instance, especially the ones of the sizes that we're running for 4 straight days would not go well. We would go over budget quite quickly. So there are a lot of downsides to that. So given everything I just said, is there anybody who wants to attempt doing that? Because I'll give you a lot of extra credit if you do manage to do it.
Like you've already put that in SQL, maybe we don't have to get to before like using in SQL.
No, you would download the raw SQL dumps. So you'd have to figure out where do those dumps live. You'd have to download them, extract them, move them into MySQL, export them, and then move them into S3. Yeah, the whole kit and caboodle, end to end. That took them 2 weeks. It was a pain. But it also means I can help you, but I won't be able to make myself that available for working on this because I have to prioritize helping people who are working on project 2. Since this would be just an extra credit assignment. So those are the two options I'm giving you so far. Can we think of a third one? Did you find out how big that data set is? No. Nothing? You got to give me something. Because otherwise, we can just spend the next half hour talking about Project 2. And I'll just decide that this is the extra credit, even though I haven't done it for a while. And we'll just hope that it works out. Is this it? Final answer? Last call? 3, 2, 1. Okay, we're doing this. All right. So I'll put out a spec by tomorrow afternoon, detailing what I expect you to do here and telling you how many points it's going to be worth. It's probably not going to be worth more than 100 points. I'm thinking 80 points. I think the maximum this is going to move you up is 1 letter grade. All right, let's do this. I can't think of anything else other than maybe something complicated with UDFs. What if we did TF-IDF on the article and I gave you some constrained hardware? That could be interesting. It sounds like you'd rather do that. I don't know. I would have to look at how hard that is because it doesn't seem all that difficult. If I remember correctly, TF-IDF is just relative frequencies of words between documents, right? Yeah. How hard can that be? No, that's true. Well, like I said, the problem that I'm dealing with here is trying to figure out how to give you an assignment to do something that you haven't done yet. This is nice because we haven't done anything like this, at least not for real. But it's also not so important that I would insist on having this as standard class material. Because I don't think the data scientists at Count have ever done something like this, right? This is trying to do this. Okay. Do you do custom aggregations like with map partitions? And okay. Yeah, at least from my understanding, this is not something I've seen the data scientists do. So this is more of an engineering task. With TF-IDF, like, yes, it might be hard, but it's also not anything new. Can you send me the link to that data set from? Okay, I'll check it out. But for now, this is what we're gonna go with. Do we have any questions on how this is gonna work? Just on this idea or mechanism? Does everybody understand what all of these functions mean? what these four functions mean. And that's just serialization. It doesn't really matter. Does everyone understand what zero, reduce, merge, and finish are? Did we cover that adequately in the aggregations lecture, the exam review, and um the other exam review? Okay. So as long as you understand this part, you have a good foundation to build off of, and you should have the tools to do what you need to do. But I haven't shown you any of this because we don't have time. And so maybe because this is probably not going to be due until the very end of the semester. Um, if you want me to grade it earlier, I can, just to give you peace of mind where your grade is concerned. So if you turn it in early and you want me to grade it, that's fine. What was that? You would just need to have Scala installed and Spark installed with Scala. So yeah, I'll try to work on this tonight so I can help you during dead week if anybody's having trouble. Like I said, I haven't done this for a while, so no promises on how easy or hard this is going to be. Do we have any questions on that? Maybe. I'm not going to make it more than 100 points. I might make it 100 points. That's it. Okay. So there's a couple of other notes that I want to go through before we go into connected components. ChatGPT. I know that we have quite a bit of ChatGPT use among the students in this class, which I'm fine with. I didn't say you couldn't use ChatGPT in your projects. And the reason I didn't say you couldn't use it is because I think ChatGPT used properly is a very good educational tool. I've been able to do things much more easily because of generative AI and that I wouldn't have otherwise been able to do. It, in some respects, has increased my productivity a lot, and I know more because of it. It is also possible to use generative AI in a negative way that impacts your education. You can use generative AI in such a way where you don't actually know what you're doing and you will turn in code that you don't understand. So this is a PSA. I feel like I'm in alcohol advertisement. This is a PSA. Please use ChatGPT responsibly. It's okay if you want to use it to generate code. It's okay if you want to use it to check code, but do it mindfully and make sure you understand what it's telling you. And make sure you understand why it's telling you to do the things that it's telling you. Kind of like Stack Overflow, don't just copy the code. Are we okay? Good. All right. Has anybody gotten notifications for course evals? Okay. So if maybe I shouldn't say everybody, we have 13 students in this class. If at least 11 people complete the course eval, I'll give everybody a 1% bump to their grade. Huh? Yes, just 1%. Deal? Deal. All right. Get your responses in, please. Because that's important for me as a person who teaches this class. I need feedback from all of you. because Amit is on sabbatical next semester, so you all might be stuck with me if they don't find someone else to teach this class. Just remember that the teacher learns just as much, if not more, than the student. Okay. All right. I think we've talked about all the things that I wanted to talk about, so let's move on to project 2. All right. Now I understand that a lot of you want to walk through the connected components algorithm that we might use in Spark again. We want to do that? All right, let's go and do that. Okay. I wonder if there's a way I can do this on the screen so I don't lose the remote people. Yeah, I don't really like the whiteboard here. Okay, here's what I'm gonna do. I might just do it in. I have no idea what's in that. Yeah, I could. The problem is that the quality isn't that great. Um, yeah, no. Okay. So here's what I'm gonna do. I'm not gonna present this on the whiteboard. I'm just gonna do it in text. And we'll present it that way. Chat, are we okay with that? Hello?
Yeah, yes, we are okay.
All right.
Everything okay.
All right. Let's say we have a graph. And let's say this graph has five vertices. Okay. I have to decide how I'm going to lay this out. And these are going to be all the connections between different vertices in the graph. So A is going to have connections to B. I'm just going to make a B going to have a connection to A because this is going to be just an adjacency list format. And it's also going to have a connection to C. These are sets, by the way. This is set notation in Python. And this is going to have a connection to A. And also a connection to D. And for D, it's going to have a connection to C and also to E. This is going to have the connection to just D. All right. So what shape does this make? It's just a line, right? So what this looks like in practice, it's A connects to B, connects to C, connects to D. We can't do this with every topology, but we're going to do it for now. Connects to E. Okay. So here's what the connected components algorithm does. What we're going to do is I'm gonna represent this state with just another dictionary, and it's going to represent the current connected component of each vertex. And then I won't have to erase anything. I'll just copy and paste when we make a change, when we do a new iteration. Deal? Okay. So these are going to be our starting component IDs. Make sense? You can make your starting component IDs for whatever you want. You could also just make your component IDs the same as your vertex IDs to start out with. You can do however you want. Right now, we're going to use separate component IDs just to make everything clear. But we could also make the component IDs A, B, C, D, and E. We don't care. Okay. So we start out with this iteration, right? So here's what we do. This is initial labels or initial components. This is going to be iteration 1. All right. So we don't know what any of these are yet. This is undefined right now. So what we're going to do is we are going to take all of the edges or all of the connections for every node, look at the neighbors of every node, and then adopt the minimum value for actually what we should do is we should add like a second connected component somewhere so we can see how this works, because this is not a good illustration of how this is going to function. And we should actually switch things up a little bit. What we're going to do is we're going to change this, not that. We're going to change this to 3 and this to 1, just so that this goes a little bit faster. Is everybody good with that? Okay. So we have F and G. No, G connects to F. Okay. This is much harder to do in text. Okay. And so we expect these things to work out to different connected components. We're going to represent our connected components as sets. So all of our components are going to be represented like this. You remember the frozen set from the Project 2 demo? Okay. So we're going to have a frozen set of frozen sets. How much time do we have? Ooh, we only have 15 minutes left. Okay. Well, I can extend this into office hours if we want. So we're going to have one frozen set of A, B, C, D, and E. And then the other, what's the other one? Yep. What else? F and G. Okay. All right. So this is the end result. This is what we want. So in iteration 1, so what we're going to do is F6, G7. Okay. So here's how this is going to work. We will initially go through all of these vertices and look at all that vertex's neighbors. And when we do that, we will adopt the minimum value from the minimum of the current label that we have and all of the other surrounding labels. So that way things will just kind of collapse as we iterate. Make sense? We'll do this iteration by iteration, then it'll make sense. Okay. So let's look at the first iteration. So when we have the initial components, let's just set here. Okay. So when we have the initial components, we're just going to go through down the list. All right. What's A connected to? What are A's neighbors? B. That's the only neighbor for A, right? And so what's the current component value of B? It's 2. So we're going to change this to 2 because 2 is lower than 3, right? Right. All right. And we move on to B. Now just remember, as far as B is concerned, because this is Spark and we do things iteratively, A is still 3 and not 2. So you cannot look at the current iteration. You're always looking at the previous iteration. That's what we have to pretend like we're doing here. So as far as B is concerned, this hasn't happened yet. This update of A having a component ID of 2 hasn't happened yet. So B will go and look at its neighbors, which are what? A and C. So it'll look at A, which is 3, and it'll look at C, which is 1, and it'll look at itself, which is 2. What's the lowest out of those 3? 1. So we update this to 1. All right. Now we move on to C. What's C going to do? It's going to look at all of its neighbors. What are C's neighbors? B and D. Okay. So what are the component IDs associated with B and D? 1, 2, and 4. So C itself is labeled as 1, B is labeled as 2, and D is labeled as 4. What's the lowest out of those things? 1. So C doesn't change because it's already the lowest. So we move on. And we move on to D in this iteration. What are D's neighbors? C and E. What are the IDs associated with those? 1, 4, and 5. D has 4, the neighbor C has 1, and the neighbor E has 5. What's the lowest? 1. So we're going to change this to 1. Okay. E, what are its neighbors? D and F. Or no, just D. Just D. All right. Now, what are the values that it's looking at? 4 and 5. It's just these two. It doesn't know that D has updated to 1 yet. So 4 and 5, which is lower? 4. So we update E to 4. That's this iteration. So now we move on to F. What are F's neighbors? Just G. Okay, what's the value associated with G? What's the component ID? 7. What's the component ID for F? So those are the two values we're comparing, 6 and 7, which is the lowest? 6. So this doesn't change. Then we move on to G. And G is going to look at its neighbors, which is what? F. Okay, what's the value for F? Okay, so what values are we comparing? And what's the lowest? Great, so we change this to 6. That's iteration 1. Now we go with iteration 2. Okay, so we'll look at A. What are A's neighbors? B. Okay, what values is it comparing? 1 and 2, which is lower? Okay. Now, we look at B. What are its neighbors? What values is it comparing? 1 and 2. So what do we get? 1. So this doesn't change. Then we look at C. What are its neighbors? B and D. All right. What values is it comparing? Just 1. So we don't change anything. And then we look at D. What are its neighbors? What values is it comparing? 1 and 4. So what do we get? So we don't change anything. Great. So for E, what are its neighbors? Huh? Yes. And what values is it comparing? Okay. Now, what do we get from 1 and 4? Okay. Good. Then we move on to F. What are F's neighbors? What values is it comparing? Just 6. So we don't change anything. We move on to G. What are its neighbors? What values is it comparing? 6. So we don't change anything. Now we're done. So now the only thing we do, if we wanted to put this into frozen sets, we would just say for, not from, for our vertex and component um, okay. In labels, let's just call labels dot items, which is what this is going to be over here. And we'll say um, okay. Oh, there we go. That's what we're looking for. Okay. This is just a little transform. So this is what I would use if I was writing your tests, is just this frozen set of frozen sets. Because if there's a difference in here somewhere, then your testing suite will find it. So there's like a test assertion somewhere. Oh.
It tells us difference between first and second and first.
Well, yeah, but we need like a unit test class for that. I'm trying to figure out how to do it without one. No, it's okay. It'll show you what the differences are. Does this format kind of make sense to everybody? You don't have to use a frozen set of frozen sets. You can represent your tests and your expected values however you want. This is just a suggestion. So you don't have to do it slow. So does this demonstration make sense? Is there anything else we need to talk about before the break?
When you're going through looking at what like are the daily like how would you track that dailies like start?
I would recommend keeping an edge list. So I would recommend keeping like whatchamacallit, a data frame where the two columns are source and destination. And in source, it's going to be A, and in destination, it's going to be B. And it's one pair or one edge per row. So in another example, if you were to have a data frame to represent this graph, here's what it would look like. You would have, let's say you have source and destination. These are just the column names, would be A and B. And then we would have B and A, and then B and C, and then C and B, and then C and D, and then D and C, and then D and E, and then E and D. And I also recommend keeping self loops in there too. It just makes it easier. So you can have A and A because you also need to compare A's current label with everything else. So you can keep A and A, B and B, C and C, D and D, E and E in there too. This kind of is the adjacency list because you need to do a join on both the source and the destination. Or you don't need to do a join on the source and the destination, but you will need to use the source and the destination independently. So this is what I recommend you do. Questions on how this example works? We all get it? You can use a different algorithm if you want. In fact, if you find something more efficient and implement it, I'll give you extra credit for that too. Other than this very simple iteration by iteration propagation, right? Because that's what we're doing. We move one step further out from the originating node of this lowest value in the component. There are more efficient methods to do it. Anything else? 30 seconds until break. So we're good.
It makes more sense to use the pronouns instead of getting back to that.
Does it do recursion well? That's news to me.
It's not, I mean, the idea that it is not changing the pronouns, but
Mm-hmm.
seems like it would fit.
I mean, it kind of is. Well, one thing about just writing code is that any iterative algorithm can be expressed in terms of recursion and vice versa.
You know, the thinking, communication.
Just remember that this implementation is different than um, other graph algorithms that you will see in an algorithms book. Because a lot of the time in an algorithms book with traversals like this, you are changing the state of a node. Like you mutate the state of a node when you visit it, so that when you reference it again, you know you've already visited, right? You can't really do that here, at least not easily. And so a lot of the time, every iteration, you saw this in the demo, is that every iteration will produce its own data frame. Chat, how are we feeling? I'm going to interpret that as good. All right, school's out. Have a great Thanksgiving. See you in Dead Week.